All right. So this is section 8.3 for pre-calculus. We've been talking about trigonometric functions. Just been looking at the graphs of a bunch of different trig functions, but it's time to start looking at combining the idea of trig functions with inverse functions. So first, remember uh, from chapter 3, the idea of an inverse function. You have f of x, and then you have your inverse, which is called f inverse of x, and we tend to use that -1 power notation, despite the fact that -1 power is not exactly what we're talking about. -1 power usually means reciprocate, but here we're borrowing that notation to mean inverse, like an inverse function. It means a different thing. That's still going to be true in this section. We're going to be using that -1 power to mean inverse. Okay, but remember that an inverse is basically something that undoes whatever f does, right? Like it does something like that. When you compose them together, they cancel each other out, right? They just cancel each other out, and there's whatever you put in is what you get out. Also, if you go put a triangle into the f function, right, and you get if you put a square into your f function, you get a triangle back out again. And that means that when you take a triangle and put it into your f inverse function, you're going to get a square back out. Okay, so input and output are swapping roles, right? Okay, that's just a reminder of all that inverse function ideas. So now that means that for a trig function, which I'm just gonna write the word trig, and that trig there could be replaced by sine, cosine, tangent, secant, whatever. Okay, trig functions usually interpret the input as an angle, right? And then the output is a ratio, rise over run, sine over cosine, or sorry, a ratio, opposite over hypotenuse, opposite over adjacent, adjacent over hypotenuse, hypotenuse over opposite, whatever, one of those ratios. So that means that an inverse trig function should do this. It should take the ratio as an input and then give us an angle as an output. But we have some problems. So the two problems I want to talk about today here are coterminal angles and symmetry. Okay, so let's call those 1 and 2. So let's move over here. First, 1, coterminal angles. Remember what coterminal angles are. They're angles that have the same terminal point on the unit circle. So take, for example, 5 pi over 6. 5 pi over 6 has this terminal point right here. And let's see, the coordinates of that terminal point should be, based on unit circle, negative square root of 3 over 2 and 1/2. Now that is coterminal with, for example, negative 7 pi over 6. Okay, 5 pi over 6 and negative 7 pi over 6 both terminate in exactly the same place. So the problem is, what then should be the inverse, can I spell inverse? Doesn't matter. Inverse sine. What should be the inverse sine of, say, 1/2? Right? Because you're supposed to input this number here and then get the angle back. But what angle are we going to get back? Are we going to get back 5 pi over 6? Or are we going to get back the negative 7 pi over 6? Or any one of the other infinitely many different angles that terminate at that point, right? So that's one of the problems, is what should the output be? Okay, there's tons of different inputs for the sine function, which are going to give me a value of 1/2. So which one are we going to give as an output for the inverse sine? Okay. The other issue is symmetry, right? Let's get back to 5 pi over 6 again, right? With this point here, negative root 3 over 2 comma 1/2 at 5 pi over 6. Well, 1 pi over 6 has a point at positive square root of 3 over 2 comma 1/2. And they have the same y coordinate, 1/2. So again, with symmetry here, well, what are you going to give as an output when inverse sine takes in 1/2, right? In both of these, it's like, well, we have different options for what we could give out. both of these are basically come down to the same thing, which is the problem that sine function, cosine function, tangent function, any of those trig functions, they're not one-to-one, right? If you look at the graph of one of these things, the graph of a wave is not at all one-to-one. You can draw horizontal lines that cross through at infinitely many places on graphs. So it shouldn't be invertible. It's impossible it's truly impossible to inverse the entire function. So what we're going to do is we're going to create what are called what are sort of like inverses. There's no real official term for this. I like to call them quasi inverses or partial inverses. The idea we're going to establish is that if you take, let me call this quasi inverse. If you take the sine function, if you restrict the domain and then invert it, after restricting the domain, you can make it one-to-one, and then you can invert it and get what's called sine inverse. Which actually, for sine inverse, two notations. You can write it with the -1 power like this. Okay, so just like that with a -1 power. Or since these are a little bit, these are not exact inverses for the trig functions. They're kind of like these quasi inverses, sort of restricted inverses that sort of work, but only for a certain restricted domain. Because of that, it's common to use different notation. Instead of the regular inverse notation, you use something else. And the terminology is arc trig functions. So arc sine, like that. You can do the same thing with cosine. You can call it cosine inverse, using this notation, or you can call it arc cosine. You can get arc tangent, arc cotangent, and so on and so on and so on. So that abbreviation arc is like saying inverse. Okay, sort of inverse. All right, so let's look at how this is gonna work for the function. So let's jump over here to Desmos. All right, so here's the sine function. What we want to do is restrict the domain of this sine function so that it is one-to-one. Now, there's more than one way to do that, but what we're going to do is we're going to pick what's sort of the simplest, most obvious way to restrict the domain. And the sort of guiding principle we're going with is we want to pick something that involves 0, and that if at all possible, we want it to involve angles in the first quadrant. If angles in the first quadrant, the acute angles are the angles we kind of work with most often, to be honest. So for us, to be an x values between 0 and pi/2, we really want to make sure that we include this little segment right here. Now, the other thing we need to do is make sure that we restrict the domain so that we include the entire range, right? We can't leave out any portion of the range because then you'd be leaving out possible inputs for your inverse function. So we need to capture the entire range from -1 up to 1. So the obvious thing to do here is to take this segment here. It's gonna include 0, which is nice. It's gonna include all the acute angles over here between 0 and 90 degrees, and then it's also gonna capture negative angles, which will give us all of the possible negative sine values. So that is just the one that makes the most sense. Let me restrict it here to pi/2 less than or equal to x less than or equal to positive pi/2. And there we go. So that gives us a segment of the sine function, which is now one-to-one. This now passes the horizontal line. Like I was saying earlier, this is by no means the only option. Like we could have done positive pi/2 to say 3 pi/2. That's also one-to-one, but it's just less convenient because it doesn't involve those acute angles. So we're going with the standard one. And this is standard. Like this is part of the definition. It's not just that for the sake of this class, I'm picking this interval. This is the interval that defines how we invert sine. So now, with that, I should now be able to graph x equals f of y to give me the inverse. And we see it's this purple thing, right? This is the reflection over the diagonal line. That purple graph right there, that's the graph of inverse sine. And in fact, if I graph y equals arc sine of x. Desmos knows exactly what that is. Let's get rid of these other two. And there it is. That is it. And that is corresponding with the inverse of that restricted domain sine graph that we just made. So there they are next to each other. There's the sine and there's the inverse sine. Yeah, that's how it's going to work. Okay, so our inverse sine, you can see, is going to have a different domain and range. Okay, I think I'm going to get back to that in the next video. So the next thing I want to do is do this with cosine. Okay, if we do f of x equals cosine of x, then we again want to restrict this to have a segment that's 1-to-1. So, but we want to capture these angles here, which are our acute angles. So this time, the one that makes the most sense is to capture this bit and this bit, and then use this angle, which goes from 0 to pi. So we restrict 0 less than or equal to x less than or equal to pi. There's the segment. And then if you x equals f of y, if you flip that over, that is your inverse cosine. And we can confirm y equals arc cosine of x is that little segment right there. So so there we go. There it is with cosine, and then we'll do it with tangent. There we go. Desmos tangent f of x equals tangent of x. For this one, we've got to capture the entire range. So in this one, we have to pick a segment that's going to go all the way from negative infinity to positive infinity. But we want to include the acute angles as always. So that would be this segment here. So obviously, we're just going to take this little part here. So the vertical asymptotes are going from negative infinity to positive infinity. No, sorry, I misspoke. The vertical asymptotes are at negative pi over 2 and positive pi over 2 here. So I want to take negative pi over 2 less than x less than positive pi over 2. I did less instead of less than or equal to this time because tangent actually isn't defined at those endpoints. That gives me a restricted version, which is now 1-to-1, which you can reflect and make your inverse. So that is the graph of arc tangent of x right there. Okay, so there are the three graphs. We've got, there's the graph of arc sine. There's the graph of arc cosine. Okay, arc sine, arc cosine looks like that. And then arc tangent looks like that right there.